Let's practice analyzing an open system for which the mass inflow rate is not constant. So we want to know how long it takes to fill a water container, and more specifically, we're given that there's liquid water flowing into an initially empty container of volume 5 cubic meters, but the mass inflow rate is a little complicated. So m dot in is going to be given by 2 kilograms per second times e to the t over 30 seconds. So you can see from this that initially the mass inflow rate is not that high at t equals 0, it's just 2 kilograms per second, but after even 30 or 60 seconds it starts to be much higher, so we have to account for that in figuring out how long it takes to fill the entire container. We're also told that there's no outflow, so water goes into this container but doesn't come out. And the container, you can have in mind, is something like this. Its volume is 5 cubic meters. So we just want to know how long in terms of time it takes for water to start entering before the entire container is full. Okay, we've done a problem like this before for a steady m dot, but now we have a varying m dot. We need to take that into account. Let's start with the most general form of mass conservation that does apply to systems like this that have transient behaviors, namely time-dependent behaviors. That is that the mass inside our system at some time t minus the mass at time equals 0 must be the difference between the inflow mass and the exit mass. Okay, in this particular system, we can actually set two of these terms equal to 0. We say that it's initially empty. That means that m sub cv at 0 must be itself 0. Remember, CV just means control volume. That's just saying that it's our open system. So we can get rid of that second term. We can also get rid of m sub e, because in that case, we know that there's no outflow, so the total amount of mass that has exited the system must be 0. Let's simplify by getting rid of those two terms. So all this tells us is that, of course, the total amount of mass in our system at some time t is the amount of mass that has come in through the inflow. That has to be the case because it was initially empty and there's no exit. So how do we compute m sub I? Well, m sub I has to be the time integral of m dot I, right? And I've added a prime symbol to the differential there to make it dt prime. That's just to distinguish between the thing we're integrating over and the limit of integration t. It's a dummy variable, it really doesn't matter what you call it, but that lets us know that indeed we're not integrating over one of the limits of integration, which is generally a bad idea. Okay, so we know all of this, and of course we know the form for m dot sub I. There's only one trick, which is that we don't actually know the left-hand side yet, so we don't know the total amount of mass in the container. But the nice thing is we can figure that out pretty easily, because remember, the goal was to fill this container, and we know that the target volume has to be the total volume of the container, so it's 5 cubic meters. In that case, the amount of mass in a 5 cubic meter container filled with water, well, it'll just be m equals rho times v. V again is the volume. So we plug in those numbers. Rho is always about 1,000 kilograms per cubic meter for water. The volume is 5 cubic meters. Multiply those together. That tells us that we're trying to put in 5,000 kilograms into this container. So that means that the number 5,000 kilograms we can substitute in up here in the equation for mcv. So we didn't know the mass, but now we do. That's the target mass we're trying to hit by filling this container. So that must mean that 5,000 kilograms equals the integral over time of m dot I. And all I've done at the bottom is substituted in that specified form of the mass inflow rate. Okay, so now all we have to do is solve this integral and then hopefully find a way to isolate t. So let's move this up. We'll simplify things a little bit by pulling out the constant part of that, the 2 kilograms per second. Okay, now we just have an integral from 0 to t of e to the t prime over 30 seconds dt prime. Okay, well, let's divide through by 2 kilograms per second first. So we get that 2,500 seconds over on the left-hand side. Now we can do this integral. If you want to do it in your head, you probably can. You can also use a simple substitution. Let's come up with a dummy variable mu that is t prime over 30 seconds. That gives us a d mu, and we'll substitute all that into the integral. So we do that. 2,500 seconds equals this new integral. I changed one of the limits of integration. Remember, you have to do that with the substitution for a definite integral. So it now goes from 0 to t over 30 seconds, but now it's just e to the mu. And we have a constant of 30 seconds out there, d mu. So we can pull that constant out. All right, we'll divide both sides by 30 seconds. That gives us 83.33 unitless. Must equal, and now I've evaluated the integral, e to the t over 30 seconds minus e to the 0. Remember, the 0 term is not itself 0. E to the 0 is 1. Okay, so we'll move that up. Let's write that explicitly so we don't forget about e to the 0. That tells us that we can move the 1 over to the left-hand side and get 84.33, again unitless, must be e to the t over 30 seconds. Alright, we can solve this for t. Let's take the natural log of both sides. We do that, and the ln of 84.33 is t over 30 seconds. Multiply both sides by 30 seconds. I feel like we've done that before. And t equals 30 seconds times the natural log of 84.33. Solve that, and you get that time equals 133 seconds. So that's the amount of time it takes to fill this container. Now the interesting thing is that actually, if you look at the mass inflow rate, so it's just a little over 2 minutes to fill this thing up, the mass inflow rate at t equals 0 is 2 kilograms per second. The mass inflow rate, as you start to get up to 133 seconds, is more than 80 times that. So most of the mass actually enters right before t equals 133 seconds. The mass inflow rate shoots up so dramatically because it's an exponential that a lot of the water's mass comes in right at the end of the process. But in total, it takes about 133 seconds to fill a container of 5 cubic meters with that specified inflow rate.